You're listening to Würth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're checking in with leading industry experts and our very own Würth Elektronik specialists. We're going to shine a light on interesting topics like energy harvesting, wireless power transfer, we got some EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast. In this episode, we are circling back to our discussion and our debate on gallium nitride, or GaN, versus silicon carbide, SiC power devices, and what's going to work better in soft switching. Now, gallium nitride, or GaN, is a wide bandgap compound semiconductor, and it's formed by the combination of gallium and nitrogen in an atomic structure of quartzite crystal. Due to its 3.4 electron volt band gap, it can actually be used in optoelectronics like blue LEDs and violet laser diodes, also high power and high frequency devices. Since the early 2020, there has been an increasing use of GaN power transistors in power supplies. Capable of high breakdown strength, fast switching frequencies, high thermal conductivity, and very low on-resistance devices that are based on GaN show increasing performance compared to silicon-based devices. Now, all these parameters translate into increased efficiency and component size shrinkage, therefore reducing the cost of many power conversion systems and final products. Now, when we compare silicon carbide or SiC power devices that have been around for quite a while now, GaN power devices have just started to appear on the market. GaN offers many of the performance benefits of SiC with the prospect of accrued competitiveness because it's grown on a larger, low-cost size substrate, and it can be produced in renovated CMOS fabs. However, the technologies that are used in SiC and GaN power switches are really different. The SiC, for instance, is a harder material, and it requires more sophisticated manufacturing techniques at a far higher temperature with respect to silicone. Annealing is done at 1,700 degrees Celsius, and ion implementation at 500 degrees Celsius, compared to 800 degrees Celsius and 25 degrees Celsius, respectively. GaN switches, on the other hand, are derived from RF HEMT, or high electron mobility transistors technology, which is different from that of silicon power FET. A summary of the parameters for each technology can be shown in our first table. A couple of the major differences we see in this table include the band gap, and for silicon this is 1.1, SiC 4H is 3.2, and GaN is 3.4 electron volts. And we also see the breakdown electrical field E sub BR, which is the electrical breakdown. For silicon this is 0.3, SiC 4H is 3, and GaN is 3.5 megavolts per centimeter. Now, SiC MOSFETs and GaN HEMTs are largely complementary, as each one of them addresses different applications. Electric vehicles are benefiting from these large-scale adoption of both, with SiC MOSFETs and their ability to operate at voltages between 650 volts and 2,200 volts, being ideal for traction inverters, DC-to-DC converters, and onboard chargers, or OBC. Operating at voltages from 650 volts down to 100 volts, we're seeing that GaN may eventually be a valuable technology for these latter two applications. And this is because of its higher frequency capability as it becomes more mature and cost-effective. As a key supplier of power solutions, STMicroelectronics has heightened efforts to complement its offer with wide bandgap materials, or WBG, and this includes silicon carbide and gallium nitride. The MasterGaN series is a more advanced power system in package, integrating a gate driver and two enhancement mode GaN transistors in half-bridge configuration. This also features UVLO protection on both the lower and upper driving sections, preventing the power switches from operating in low efficiency or dangerous conditions, and the interlocking function avoids cross-conduction conditions. The input pin's extended range allows easy interfacing with microcontrollers and DSP units. The series operates in the industrial temperature range, which is -40 degrees Celsius up to 125 degrees Celsius, and the devices are available in compact 9x9mm QFN packages. STMicroelectronics MasterGaN platform includes MasterGaN 1, MasterGaN 2, MasterGaN 3, MasterGaN 4, and MasterGaN 5 available, all with different RD Sun of GaN transistor, static drain source on resistance, and this helps to better address specific application requirements. To help developers evaluate the characteristics of MasterGaN platform and to quickly create a new topology without the need of completing PCB design, a demonstration board is available for each MasterGaN device. In our next table, we see the typical applications suited for each MasterGaN family. And for MasterGaN 1, the typical application includes OLED TV, LED lighting, adapter, telecom server power, power supply for 5G. MasterGaN 2, we are seeing fast and wireless charging, AC to DC adapters, USB PD. The same goes for MasterGaN 3, fast and wireless charging, AC to DC adapters, USB PD. For MasterGaN 4, applications include LED lighting, power for PC, power supply for 5G, and finally, MasterGaN 5 applications include AC to DC adapters, USB PD, and LED lighting. So based on our original table, the one that compares the silicon, SiC4H, and the GaN parameters, wide electron mobility and wide bandgap materials are already objective indicators of the superior performance of the GaN-based devices in certain applications. However, we need to see the benefits in real applications, and there are other important electrical parameters that we need to explore. For example, GaN transistors have a much lower gate charge. To charge intrinsic capacitances of gate-generated losses in the gate driver, gate turn-on-off resistors, and the internal structure of transistor. These losses can be calculated in a fairly easy equation. It's P sub gate charge equals FSW times VCC times QG. Now, where FSW is the switching frequency of the converter, then we multiply that by VCC, which is the supply voltage of the gate driver, and then multiply again by QG. This is the gate charge needed to charge input capacitance of the transistor. Since the input capacitance is nonlinear, the gate charge curve can be found in almost every datasheet. In our first table, we showed a comparison of the gate charges for the corresponding transistor in SiC, silicon, and GaN MOSFET technology, and this already revealed an indication of the superior performance of GaN technology in high-frequency applications with lower gate power losses. In our next attached figure, we compare the losses caused by the gate charge from a real application. This shows the measured power loss, the VCC consumption of the gate driver IC in an LLC topology switching at 500 kHz. The comparison is made between two different SI MOSFET generations, DM6 and DM2, and the GaN-based model MasterGaN 1. Significant improvements were brought to the SI-based transistor in last superjunction generations that reduced gate losses by 32%, but comparing the best SI MOSFET at the time of comparison to the MasterGaN 1, an immediate huge difference is 80% can be noted in the reduction of gate power losses. Clearly, the high switching frequency is better suited for a GaN application in this case. Simply measuring the power consumption of the gate driving IC under the same operating conditions is just one way to directly understand the benefits of GaN over SI-based MOSFETs. Another way to understand this is taking a more scientific approach, and this is to look at the same designs with an oscilloscope probe and then measure the resonant transient in the LLC topology. A lower parasitic output capacitance allows for faster charge of the transistor and tighter control because of the lower rise times. The transient measurements that we can see here prove this by showing an almost 4 times shorter dead time for the GaN compared to the equivalent superjunction MOSFET. The results we got were from using an existing reference design for a 250 watt LLC power supply, 400 V in and 12 V out. On paper, the differences are obvious, with clear advantages on the GaN side compared to SiC-based devices. But is there any difference when it comes to application type or power topology? There are many factors to consider when choosing one technology over the other, like the final application, the power topology used for the converter, and the passive elements around the switching converter. So is it useful to select GaN if the design requirement is 100 kilohertz switching frequency, resonant topology, and there's no need for a high density? So to answer this as effectively as possible, we needed a direct comparison to be made with a real application. So here, Würth Elektronik, as a passive component manufacturer, joined forces with our very valued partner, STMicroelectronics, and in a small research project, we considered this topic. First, 2 LLC power supplies were chosen for analysis. We have a 250 watt, 350 volt to 15 volt converter with a very convenient switching frequency of around 110 kilohertz. And second, a 200 watt, 350 volt to 15 volt converter with a higher operating frequency of 370 kilohertz. 2 different LLC transformers were used to further evaluate the differences, specifically designed for this performance benchmark. Before we go into the test results, we're going to take a look at an LLC topology and test setup. In our next attached image, we are seeing a simplified schematic of LLC power topology used for our testing. In the center of the figure, there are 3 elements at the heart of the circuit. The resonant tank formed by the resonant inductor, LR, the magnetizing inductor, LM, and resonant capacitor, CR. The resonant inductor is usually integrated into LLC transformer established by leakage inductance. Further efficiency tests were conducted for an output power of 150 watts, 200 watts, and 250 watts with GaN and SiC-based. First, with a comparison of efficiency at low switching frequency of 110 kilohertz, and an off-the-shelf standard transformer. And then we took the 370 kilohertz frequency with a much smaller transformer optimized for the increased operating frequency. A summary and overview of the boards and the results are shown in our attachment. The test shows that for a low switching frequency, as expected from our theory, there's no relevant difference between SiC and GaN-based devices. Now, on the other hand, increasing the frequency, which in turn also allows us to decrease the size and the inductance of the transformer, resulted in a 4% increase in efficiency by using GaN at 150 watts. At 200 watt output, the GaN still achieves a higher efficiency with a higher switching frequency compared to the SiC, even if it's just a 2% increase. At lower switching frequencies, the difference between SiC and GaN is small for every power output. An advantage of using a higher switching frequency can be noted in the size of the transformer, which in turn translate to decreased losses in the transformer as well, not just for the MOSFET or the gate driving IC. The volume ratio between the 2 transformers is 1 to 3.5. In our next attached image, we have infrared measurements at different points on the evaluation boards running at 370 kilohertz switching and 200 watts output power. More so, a small size means a smaller PCB or the possibility of high-density designs further optimizing costs. The LLC topology can be used in a wide variety of power levels, which in turn influence factors like EMC input filter, output filtering capacitor, and the use of an external resonant inductor, or the transformer built with an integrated resonant inductor by using the leakage inductance. All of these topics are actually covered by Würth Elektronik's extensive portfolio, ranging from EMC solutions, inductors, and capacitors to custom design magnetic capabilities. A wide variety of solutions for the EMI filtering are possible, ranging from the use of more common mode chokes with nickel-zinc, magnesium-zinc, nickel-zinc plus magnesium-zinc, or nanocrystalline core materials for a variety of attenuation factors over a broad frequency range, to the use of ferrite beads, filter chokes, and hybrid polymer capacitors. The HCFT with either flat wire or round wire is actually an excellent candidate for the external resonant inductor in the LLC topology, or if a Litz wire for low AC losses is needed, then you could choose from the HCF series. Further improvements to the off-the-shelf parts can actually be made depending on the requirements through the custom magnetic service we offer. With increasing power, the need for isolated drivers becomes even more important to ensure efficient and robust driving of GaN devices or even SiC devices. For the isolated driving, ST offers galvanically isolated gate driver family called STGAP or STGAP. To properly operate these gate drivers, the isolated auxiliary supply is needed. Würth Elektronik developed a new series of auxiliary gate supply transformers, the AGDT series. This offers ultra-low interwinding capacitances, ideally suited to keep the parasitic capacitances barrier as low as possible in order to maximize common mode transient immunity and keep the noise from coupling from high voltage side to low voltage side. Combined with ST's synchronous ISO buck converter L6986L or the latest L6983L offers excellent solution to gate drive or SiC transistors. In conclusion, the new GaN technology allows us to achieve soft switching converters at higher switching frequencies. There are two reasons why the higher frequencies are possible. This is lower gate charge and smaller parasitic output capacitance of GaN transistors. With the increase in switching frequency, the designer has the advantage of a reduced board area by reducing the size of the main transformer, which allows the engineer to design higher power densities in the same area compared to SiC-based devices. However, the low input capacitance of GaN transistors tends to be pretty sensitive to any noise, and therefore more care must be given to the layout around the main switching loop due to the higher switching speeds. On the other hand, looking at the direct comparison between SiC and GaN, at lower switching frequencies, we notice that there's really no benefit in using GaN for now. This would only increase the cost, resulting in a poor ratio of efficiency versus cost. If high switching speeds and high power density are not the main requirements, then it's still better to go with a SiC-based device. Moreover, why bother with the EMI issues associated with high switching speeds if it's not entirely necessary? Nevertheless, STMicroelectronics and Würth Elektronik are here to provide you with a complete solution from both active and passive side, with experts ready to support your implementation of GaN devices with the best transformers and inductors to squeeze the last ounce of efficiency out of the design. We encourage you to check out the complete lineup of EMC solutions, inductors, and capacitors from Würth Elektronik. Find it all at www.we-online.com. Make sure you click that chat icon to talk with a live Würth Elektronik person for any questions you might have. You can also download this complete article and more, available at All About Circuits, a very valuable partner of Würth Elektronik. Visit www.allaboutscircuits.com. We understand that some videos and images are not available on all streaming networks. To replay the entire podcast with video, please visit our website at www.we-online.com/podcast or check out the Würth Elektronik YouTube page. You're listening to Würth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik tech specialists who will shine a light on interesting topics. such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.